Well, happy Thursday, friends, or whatever it is when you are watching this Thursday here. And that means it's our last class of the week. This is the end of week 4. And we started entropy last time. We'll get into it a little bit more today and do a little bit more on heat engine cycles. But first, a couple of reminders. We have PLC 4 for this week for Friday. That's tomorrow. At least here it is. PLC 4 is Friday. Um, homework uh, homework 2 and quiz 2 were yesterday, so hopefully those went fine. We'll have lab 4 tomorrow. At least I will be posting and doing the intro stuff tomorrow so that you can do that at your leisure. And I will get homework 3 posted up a little bit later today, I think. And this will be, so homework set 3 will be probably the last one before the first celebration. And I'm thinking that's going to get rolled out on, let's see, I think if I look in the syllabus, I think I said March 11th. But let me just take a quick look at the syllabus here to make sure that that's what I've got. Yes, March 11th. So that's a Tuesday, and that means it will be 2 weeks from this past Tuesday, or 1 week from next Tuesday. Okay, we've got the end of February coming up here. This is the 27th. That means tomorrow's the 28th. And what year is this? 25. So it's not a leap year. So Saturday will be March 1st, and all of a sudden we've done 2 months in 2025 already. So first celebration coming in a week from next Tuesday. So please be ready for that. This is 3/11, and that's a week on Tuesday. That is that's the day when we will not have any class going. It'll just be do the celebration and be done. And we'll get on class starting on the Wednesday of that week. So we'll have enough time to complete plenty of talking about entropy and looking at heat engine cycles, refrigerators, and a little bit of statistical interpretation as time goes on. So before we reach that, we should be, and that'll give us all of next week. So we should be pretty well good to go by the time that hits, and that that will mark the end of our thermodynamics. And then we're going to move into optics from there. So, all right. All too short and all too brief, but that's where we're at. Okay, so just a little update on the scheduling. I do try to keep it to about 5 weeks or so each section. We're going to do thermo first 5, optics second 5, and modern physics last 5. Hopefully we work that out and it goes fine. We're going to do a little bit more on entropy here. Continuing on where we left off from last time. So I had set up the second law statements, and we've done a little bit of showing how they were equivalent. And when I say a little bit, I mean we took one special case of a disallowed Carnot cycle. There are many disallowed Carnot cycles. I only took one of them. So I was able to show that at least that one is, with that case, it's equivalent to the Carnot statement is equivalent to the Clausius statement. And we showed the Clausius equivalent to Carnot. So we're hopefully fairly well convinced those two statements are equivalent. And there's a couple other things I wanted to do about reversibility, but I'm going to put those off until maybe later today. I'm going to finish off doing a little bit of entropy, and hopefully you were able to get a good start on the PLC for this week if you so chose, with the info on entropy that we were able to do last time. Now, let me kind of just re-go through some of this stuff one more time. So entropy, I told you before, it's a measure of the disorder of a system. And a lot of books, a lot of websites, a lot of general thinking will tell you that, in fact, the second law of thermodynamics is centered around this, that it's the law of increase of disorders in systems. And it's technically not. However, it is a consequence of both the first and the second laws. How entropy comes around is a bit more of it's probably a bit more than we have time to do. So why do we have entropy? Well, let me put that off until probably Tuesday next week. Why is this interesting as a quantity? And how did it come about? We'll breeze through a little bit of that. But for right now, this is kind of like we're hitting the main high points because that's really all we can do in this time frame. It's a measure of the disorder of a system. It is a state variable. This is something I think I did not mention last time. It's a state variable, just in the same way that pressure, volume, temperature, energy, internal energy, all these things are state variables. E internal, etc. Right? These are all state variables. In other words, on a PV diagram, it has a definite value here, and it has a definite value here. Now, remember, the first law has the job of relating state variables in the form of the internal energy to the process variables in the form of the heat transferred and the work done. Okay, so the heat transferred and the work done are path dependent, whereas these variables are not. They are state variables, and it just depends on, I've got this here, I've got this here, and that's the way it is, right? Just like the gravitational potential energy, you would say, well, I'm going to have this thing here, and then I'm going to raise it up to here. If I go like this, well, that's fine. If I go like this, well, I haven't changed the difference in the gravitational potential energy. It's still this. I just had to do a lot more stuff in order to get it here. So I did more work, and I heated up and had to do all of this wiggly motion to get up here, and I can do all sorts of different paths. So the energy that I expend is different than the energy that the pen attains by going from here to here. Okay, and it's the same thing with these. The state variables are always just here to here, and the path, like the heat and the work dependent variables, like that depend, right? That's where all of this stuff comes in, and you do more work or you have to transfer more heat depending on the path that you take to go from one to the other. And I gave you a mathematical definition for this as the change in the entropy. And the entropy is, by the way, known as S. The change in the entropy is dependent on the heat that's transferred. So the heat is the thing that increases the amount of disorder in a system. So when we look at how does the entropy change, then it's predicated on how much heat was transferred. So we would say that delta S is the integration of dq over t. Now, you say, oh, well, that's great. So we have a mathematical way of thinking about it. So now we know what the entropy is. Well, conceptually, entropy is a much more difficult quantity to get your hands on. And you'd say, oh, well, it's just this. That's like saying that the work is just integral of FDS. Oh, it's just all you got to do is integrate, or uh, or whatever. I mean, it's like anything in physics, right? Where you just go, oh, it's just this, and then you find out, actually, it's got a lot more stuff wrapped up in it, and it's the same situation with entropy, big time. You think, oh, well, it's just this, but there's so much wrapped up into it. And unfortunately, we don't have a lot of time to go through a lot of the cool things that about entropy that uh, that are helpful in shaping your mentality about it. And one of the things I was talking about with the live class yesterday was that even just taking a situation like the universe, okay, the universe, our largest possible system, it began, however many 14 billion years ago ish. And for the first 700,000 years or so, it was basically a big soup. It was a soup of particles just moving around, hitting each other, annihilating, creating, photons hitting electrons and quarks and leptons and all this stuff, eventually coalescing into protons and stuff like this. Well, as this soup evolves in time, okay, this seems to be a fairly disordered affair. Yeah? If you think about the early universe, and I bring this up as a question to show what an interesting quantity entropy is. You think of this early universe, fairly disordered seeming, right? Um, Particles flying around of their own will, banging over here, bashing here, hitting that, coalescing this, doing that, right? Just willy-nilly doing whatever, right? It's seemingly a jumble. So as much disorder as there is here, think about then what happens as the universe evolves, okay? All of a sudden stars come into play, and stars are not disordered because they are clumps, right? And now they're separated by a large space between another clump. And doesn't that seem like it's a little bit more ordered? And now go further forward in time. And now there are planets evolving. And now there are beings walking around on this planet. Are we fairly ordered as a system? I would tend to think we are. Because, even from the exterior, right? You'd notice if a little bit of me was out of place. You'd notice if my ear was over here, right? What if my ears were down here, right? That's not a very big difference, but apparently it is because they're over here. So what if my eyeballs were vertically instead of horizontal? Right? Well, so uh, we are very carefully put together. We seem to be fairly ordered, and that's all the way down to the genetics of the thing, right? If you have this protein here instead of over here, then all of a sudden you are not a person anymore. You're a goat or whatever. I don't know, but right, this is different. This is even small differences in how things are put together molecularly make a big difference to what the outcome is. So we are a quite ordered system. So how does the universe go from this disordered seeming jumbled mess into what appears to be a fairly organized system? If we think of entropy as always increasing, doesn't that seem to go the wrong way? That's a strange thing. And this is ultimately all part of developing how do you think about entropy. So these questions are not easy, and entropy is not an easy concept and not an easy quantity to get your minds around. And I think I mentioned this on the first day. The first time through thermodynamics, you go, oh, please, is there anything that's easier than this? This is so ridiculous. Anybody gets this. And then you go through it another time and you go, oh, hold on a sec. It turns out I don't understand this or this or this or this. And now all of a sudden you're in a mental crisis because I don't understand any of this stuff. And then you go through it the third time and you go, oh, well, that's just kind of like it was before. I still don't understand it, but at least I'm used to it now. And that's kind of how it goes. Um, so with the idea of entropy and with the idea of the change in the entropy, the the idea of entropy increasing or at least not decreasing is a consequence of fiddling around with the conceptualities of the first law and the second law. If we take and use laws 1 and 2, and this is part of where I'm skimping big time. Yeah, I'm just going to kind of tell you that you use laws 1 and 2 to figure out stuff like this, and you'll find that there's an inequality. And this becomes a statement of basic thermodynamics, that the entropy does not decrease. And we write that in the form of delta S being greater than or equal to 0. And this is just exactly like the thinking of energy, but only one way. In other words, if, for example, we pick a system and you say, oh, wait a second, right? I pick a system, I'm going to say, I just need to pick a system. Here, let's pick a system. Here's a system. Okay, my system is my pen. My pen, okay. Well, this is not my pen. I wouldn't do this to my pen. I'd do it to the college's pen. This pen, if this is the only thing I'm looking at, right, and I'm ignoring everything else, I look at the pen and I go, it just picked up speed, right? The pen suddenly increased in kinetic energy. There is a sudden increase in the kinetic energy. So I started with 0 kinetic energy here, and by the time it got here, it had more kinetic energy. And therefore, all of a sudden, this kinetic energy is coming from where? From just, it just grabbed energy and decided to say, oh, I'm going to start moving. Okay, this is classic of 4A problems, right? Where you go, oh, well, no, there was work done on it because there's a force pulling it. And you say, oh, there was a force that was external to the pen because the only thing I'm looking at is the pen. There's a force external to this. It's supplied by Earth. Or, if you like, the other part of the reasoning would be, my system was incomplete. It does not seem as though energy is conserved here for this system. And therefore, my system is too small. I need to include more interacting things. If I include Earth, now I understand that this has a potential energy due to gravity. And that decreases as it goes this way, and that's how I conserve energy because energy increases, right? And they just go like this. So the same thing happens with this. If you find a system in which the entropy has decreased, then you can be fairly confident that your system is not including everything. Because as far as we know, right, as far as we've figured, that conservation of energy seems to be true for almost any situation. We haven't found a violation of energy conservation. And I would say yet, because maybe one day we will. We have certainly never found a violation of this. This seems to be a very watertight description of what's going on and carries more weight to it than the energy conservation does, in fact. So a violation of this has enormous consequences. Violation of conservation of energy has us going, that's weird. Violation of this and everyone's going nuts, right? So if you find that you have a situation in which entropy has decreased, then your system has interacted with another system that you haven't looked at, right? And the entropy in that system must have increased more, or at least equal to the decrease in the system that you were looking at. So that's what I mean by a little bit of system processing, system thinking as with energy. Let's take a look at a quick example here with how to calculate and think about entropy for some regular processes. I thought of doing this. I thought of doing a kind of a nifty example, and then I thought, well, I'll just do a regular example instead. Um, so we'll do this. I'm going to do a water droplet. I'm going to take, for example, a 1 gram water droplet, and we're just going to take this 1 gram water droplet from 5 centigrade to 0 centigrade, and then to -5 centigrade. And we're going to try and calculate what is the entropy change of the water droplet. The water droplet starts at T initial of +5 centigrade and ends at T final of -5 centigrade. And in between that, it goes through the freezing point and the freezing process. So what we can do here is I'm just gonna plot this out really quickly. Here's the temperature and the time, and I'm gonna just assume that we have basically a freezer operating or something like that. So the temperature starting at +5 centigrade and dropping, and then freezing, and then dropping like this. All right. If I'm careful, well, I'm obviously not so careful. I should probably steepen that one out a little bit compared to that one. We'll have 2 phases. We'll have the liquid phase over here. We'll have the ice phase over here. They will have different specific heats to them, and we'll just keep an eye on that. But nonetheless, I want to see if we can calculate what is the change in entropy for this whole process as it starts at +5 and comes all the way down to -5. So let's look at first the sensible heat, or the specific heat, going from +5 centigrade to 0 means that since it's a sensible heat, or what I call sensible heat, right? The heat came out and the temperature changed. That's sensible. That makes sense. I'm going to go with a 1 gram water droplet. Let's suppose that our mass is a 1 gram water droplet. This is in the liquid phase. So our liquid water specific heat should be about 4.2 joules for every gram and for every degree centigrade. And the delta T is final is 0, initial is 5. No, final, yes, final is 0, initial is 5. Yeah, that's right. 0 -5 centigrades. And so we're going to come out with a fairly straightforward number here. We can do essentially the same process, right? In thinking of the heat transfer as we go from ice at 0 to ice at -5. Okay? So this would be how you calculate the heat. Now, the issue here is when I'm calculating the change in the entropy, I don't have a constant temperature, right? I've got a changing temperature. So I have to be careful in thinking about this integration, because if the temperature is not constant, it can't come out of the integration. I have to actually put this into the integral in the way that I can, gosh, what am I trying to say here? I got to put this in the integral so that I can deal with the changing temperature. That's what I'm trying to say. So if I'm taking this Q and I want to think about a dQ, a small itty bitty piece of heat that was transferred decreased the temperature of the water droplet by a small itty bit. And that means that I've done a dt-sized temperature change for a DQ sized heat transfer. Hopefully that makes reasonable sense given that we had kind of started with this whole shebang here. If I do that, I'm going to take a delta S, and I'll call this for process number one. Here's number one, here's number two, here's number three. So delta S for process one would then be the integral. I'm going to add up all my differential slices of going through here and going, I'm at different temperature, I'm at different temperature. How much heat am I removing? I'm removing MC dt over T in order to find the entropy change. I'm going to note that my integration is over T, so my limit should be T-based. And that means I should start at T initial and end at T final. And that means I'm starting at 5 centigrade here and ending at 0 centigrade up here. So delta S1, actually, let's do it over here and not over there. Okay, so delta S1 from over there is then going to be, you can see that the mass is going to stay the same and the specific heat would stay the same because it's liquid water dropping in temperature. So these two can remove, and I've got an integral of dt over t, which is log of t. I should be able to write mc times natural log of t final over t initial, like so. Now that should be true for both the sensible heat transfers that I have going here, 1 and 3. It's just that I'm going to use a different C for the two processes, all right? Once I have the form, I can write delta S3 in the exact same form, but with a C of ice instead of C of liquid water. So I'm going to say that's equal to delta S3, but I just need to make sure that I'm taking care of the C when I do that. If I want to now think about delta S2, this is where we breathe a sigh of relief because we've done the hard work already by integrating the sensible heat. Now I have a situation where the temperature is constant. I can see that right here on my graph. As the water droplet freezes, I'm going to say this is all at 0 centigrade. And so that temperature is constant, and I can remove that from the integral. And then I have the integral of dq. But because this is a latent heat process, we know how to calculate the Q. It's just the mass times the latent heat per mass, okay? So this ends up being ml divided by T for the state change process. And that would be true in general for any state change process. Doesn't matter the substance, it just matters knowing the temperature, the mass, and the L, and using the delta S and the dq over T. So that will work out for any state change. Okay. Now, if I want to calculate this though, I know that it's at 0 centigrade, so I'm going to be dividing by 0 here. So the entropy change seems like it's going to be fairly large. Maybe I should cheat a little bit and say actually the temperature of freezing was maybe like 0.1 centigrade or something like that, so I can get a number in here like 0.1 instead of 0. Maybe that would be better, because this seems like it's going to be a fairly big. Yeah, that's funny, isn't it? And furthermore, with that, we know that the heat's leaving the water droplet. So in addition to all of this stuff, I do actually have the ability to put a negative sign in here, because that heat is leaving. So this is going to be really great for us because it's going to decrease the entropy. The entropy change to be negative infinity if I put 0 in here. So we have a lot of room to play with. We can, if freezing water has a negative infinity entropy change, well then, that's great. We can fill in entropy. We can make entropy without cost. All we got to do is freeze a little bit of water, and all of a sudden we can take away all this entropy that we've generated over time, right? Or is there something wrong with this? Have I done something wrong here? No, probably not. Negative infinity. That's always a good sign. What's the problem? What's the problem here? What am I supposed to be doing with this T? Right? I'm supposed to be in, this is a T, not a delta. So I'm supposed to be in absolute units here, or absolute quantities. I'm supposed to be in Kelvin, not centigrades. Something to be aware of. So this for water freezing, 273. What I'm going to do now is I can total all these up and find the total delta S by saying it's the sum of all the individual changes. And therefore, I have these two forms for my three processes here. And for delta S1, I'm going to use this, MC, C of water, natural log. And I'm just going to put the numbers in for the temperatures here. So I'm going to use, right, 5 centigrade. No, remember, I'm not using 0 and 5 centigrade here because that would again give me a log of 0. And I think that's a fairly good red flag to have set. So if I have a T final of 0 and a T initial of 5, I have a log of 0. Also something equal to negative infinity, and therefore that's problematic. So we're going to switch to 273 over 278. Is that what we got here? Yeah. So we're going to switch the log of 273 over 278. That's the initial temperature to final temperature. Now, I'm doing this because I want to highlight something, and that is that this fraction is a number that's less than 1. We're going to take the natural log of a number less than 1, which means it's inherently a negative number, okay? So when I think of the heat that's transferred in or out of something via a sensible transfer, I already have the minus built in here. Okay, I can say, oh, what's the heat that's transferred? Well, I'm going to see that 0 to 5, or should I say 5 to 0, comes out with a negative sign here. And when I calculate the entropy change, it's going to come out negative. This is inherently a negative number, and so this is telling you the entropy during that process decreased. Okay? We will find the exact same thing during stage 3 where the ice decreases in temperature. The entropy change will come out inherently negative. I don't have to do anything to have that happen, but I do have to do something here with the latent heat transfer. I have to put that minus sign in there because we all know that Q equals ml for a latent heat. But be careful, right? If we think latent heat for boiling, well, that's heat that we're supplying. Here in this case, right, and if it's supplied to the system, then it's positive because the system is receiving energy. And in the other case, if it's leaving the system, then we have to put that minus sign in there. It's not automatically generated. Okay, so this is just a thing to look out for, that it's a responsibility that lies with us. Whereas over here, it's already built in. Okay, so make sure we're aware of that. I'm going to have this. I'm going to have a plus negative ml over t, and that's t of 273. And then I'm going to have a plus of the exact same thing, but now with ice, log of, now I have the initial temperature of freezing and the final temperature of negative 5 centigrade. So I should have final temperature goes on the top. So that'll be 268. And this should be 273. Let's see, did I run out of room on that one? Ooh, squeezed it in there. Okay, 268 over 273. All right. Now this turns out to be some number. But I hope that you will notice that there's a very interesting thing happening here. If I say well, yeah, it turns out to be whatever, yeah, it's whatever it is. The mass of 1 gram, you can calculate this number if you like, 4.2 joules per gram per centigrade, and or per Kelvin, I really should say, because we're using kelvins now. Kelvins. And this thing here, since it's ice, is about half that of liquid, so it's 2.1 joules per gram per Kelvin. And so you can go through and calculate this number. I don't think there's any light. There's no gleaming end to this in terms of, oh, we're going to gain so much physical understanding by calculating this number. Nobody really cares. But the setup of the thing is what is really important. All right. And ultimately, the figuring of the entropy change by the sensible heats and the latent heats, and knowing that you need to mind your negative signs here in the latent problem, in the latent heat, is part of this problem. All right. So we're not going to gain some huge amount of insight by calculating this, so ultimately nobody cares. But look what is true. This is ultimately a completely negative number, right? That's a negative number there because of the log. This is a negative number there because we said so, because it has to be. The heat is leaving the system. And this is also, once again, a negative number because of the log. So the entire entropy change is less than 0. We know this because of how the numbers are working out. And therefore, if we look solely at the droplet, that's the exact same thing as thinking of the pen dropping. The energy seems to come from nowhere, right? Well, the entropy seems to be disappearing out into nowhere, right? It can spontaneously, no, it can't. Because we haven't looked at where is all of this heat going. We have removed energy in the form of heat from this water droplet continuously. Excuse me. In order to reduce its temperature, in order to then change its phase into a solid, and then in order to reduce its temperature yet again, we have removed heat the entire time. Where has that heat gone? If we examine that system, I will guarantee you that that system has an entropy increase that is bigger than this. And therefore, the entropy of the droplet plus the surroundings will, in fact, be greater than 0. So it's a mentality to remember, just like it is with energy, that if energy is not conserved, we've done something that isn't quite conducive to that. Maybe my system's too small, or maybe I should have thought of that force instead as doing work, etc., etc. And so the same thing holds here. If we find the delta S being less than 0, oh, wait a second, it's because we didn't see where the heat's going. Okay, and ultimately remember that the heat that transfers is the thing that generates the entropy. So the heat that we took out of the droplet in order to drop the temperature and in order to change it into a solid, and then to reduce the temperature yet again, that energy went somewhere in the form of heat. It went into a system, and it ultimately increased that system's entropy. It must have, because of the heat transfer, right? And therefore, that entropy increase would be greater than this entropy decrease. Hopefully that's making sense. I know that if we would go by whether or not it made sense just based on the amount of hand wringing that I do, well, then it probably makes a lot of sense because I do a lot of hand wringing. So they got to do the entropy. Right? Okay. So there's that as a calculation. Now, what if we thought of just looking at basically a system through the lens of the first law, and we wanted to think about entropy change? Let's take a look at a slightly more general view, still an ideal gas, but what if we looked at the first law and we said, all right, let's calculate entropy from our of our system from a first law perspective. Okay, so the first law would tell us that the internal energy change is Q plus W. Now, through, I mean, I'm not going to sugarcoat this. Basically, through cheating, we can write it this way. If we differentialize the thing, it'll look like this. This seems to be a useful form. Maybe it is, maybe it isn't. Well, if we're interested in the entropy change of the system, remember we need the dq. So I need to take the dw and put it over on the other side. So the mirror thing is messing me up here. So the dw's got to go over on the other side so that we can isolate the dq. I'm going to get that this is internal minus dw, and we can, from there, put in a few things for an ideal gas. Okay, we know for an ideal gas a couple of things. Well, we know that the work, even if it's not an ideal gas, we know what the work is. So I should actually do this up here. We know the work is negative integral PdV. Well, actually, it's kind of that. If it's an ideal gas, we know what the internal energy change is going to look like. This dE internal, that's what we talked about last class and at the end of last week. The internal energy change depends on whether it's a monatomic gas, a diatomic gas, right? And we talked about the internal energy of an ideal gas being this number of degrees of freedom that we have times 1/2 nRT. Like this. All right. So if I take, I don't know, maybe we can take a monatomic gas or whatever you like. If I take this and we write it in a differential sense, then I'm going to assume the mole number is going to be constant because we've always worked with a constant mole number. And therefore, when I operate with a differential operator on this thing here, I'm going to take dE internal there. I'm going to go through here and use the chain rule to put together an expression for what the differential energy change is. The degrees of freedom should have no bearing on this. It's got the number of degrees of freedom that it's got. So the differential operator should pass over this. That's a constant. 1/2 is a constant. The mole number is a constant. R is a constant. And hopefully something will happen at the last one because this is it. And yes, it's T that is the thing that influences the amount of energy, right, other than mole number, which we aren't considering. T is the thing that influences the energy in the system because it's an ideal gas. So we have 1/2 nR, and we have a dt on the outside. Remembering that we can write this as the molar specific heat of the gas in a more compact way. The CV, the molar specific heat at constant volume, is this F and the 1/2 and the R. And so we could write this as N times CV times dt. I'm going to keep it this way though, because I feel like it's confusing. If I write the CV there, you'd think maybe I'm doing a constant volume process. I'm not. So I'm just going to keep it this way just to hopefully keep it clearer. Okay, we've got an ideal gas, internal energy change looks like that. We've got a work that looks like this. So we can do stuff over here. Let's do this. Now I've got a dq, so that's going to equal dE internal, which is all of this stuff. F times 1/2 nR and dt here. And I'm going to get minus plus integral. No integral. Sorry, PdV. Because I'm just working differentially here. All right, good. Okay, I'm interested in thinking about the entropy change, and therefore I would need to take this ratio, or let's write it this way. Let's write it this way first before I make it a macroscopic change. let's look at a different, since we're all in differential land, let's just look at a differential entropy change. That would be dq over t. In other words, it's all of this stuff divided by t. So I would then get f 1/2 nr dt over t. I'm going to rewrite that because I don't like the way I spaced it, and that's in the way. So I'm going to do this. All right, we're going to do this down here. ds is equal to f times 1/2 nr and dt over t. Oh, I skipped the other thing here. Let me rewrite that. ds is dq over t. Okay, and now we're going into this. So we've got 1/2 nr dt over t, and I'm going to do the pdv here. So I'm going to add on p over t dv. And since we're working within the model of an ideal gas, p over t is a thing, right? It's an ideal gas equation of state relationship that we can work with. This thing here, if I look at the ideal gas equation of state and I swap the v from the left side and I swap the t from the right side, I'm going to get n over v times r. Right? That should be what I can put in for p over t, and therefore I'm going to get all of this stuff in the front, 1/2 nr dt over t, and I'm going to get plus n over v. So this is going to be nr and dv over v. Okay. Now, at this point, you might be wondering, what the hell is going on? Haven't we been told that entropy is increased by heat? So what's with all the work? Why are we thinking about work coming into this? Work doesn't increase the entropy. It's kind of says so in the definition here, right? It's not dW here. It's not dq plus dW. It's not anything. It's just dq. It's heat only. What's going on with all of this then? Well, remembering that when we have an ideal gas process, we could have it at constant volume, right? And have a nice vertical line in which the dV is 0. And it's heat transfer only, okay? What if we have a constant pressure process, though? If we have a constant pressure process, work is getting done. But remember, though, that because work is getting done, and because the temperature has to increase, because we're crossing isotherms, right? Let's just draw a quick PV here to just put us on solid footing here. If I do a isobaric process here, and I go from 1 to 2, like that, remember that when you draw a PV graph, immediately think isotherms. So if I draw an isotherm that goes through number 1 here, it might look like that. If I draw the next one through number 2, it's going to be way over here, like that. And I think you can be fairly convinced that this T2 should be greater than T1 because of the way the isotherms increase in temperature going that way. All right? If the temperature has increased, right, we're going to go back to our ideal gas reasoning in the first law. If the temperature is increased, then I'm looking at this thing saying, oh, if the temperature is increased, I know that's a bigger number. However, the gas did work, which means it must have lost energy, right? It pushed something and did work. So in the absence of anything else, it's losing energy because it's doing work on something. It's exerting a force and through a distance on the piston, right? Yet, I have to have the ending energy being greater than the initial energy because the temperature is telling me so. I'm crossing isotherms here. Therefore, the heat that must be transferred has to be greater than the work that's getting done, right? I have to allow the system to do work and energy is leaving that way, but I ultimately have to dump in more than that in order to get the energy of the system to be higher than it was initially. Okay? So it's kind of like trying to fill a sink when the drain is letting stuff through, right? I can turn the faucet on and I can turn it on less than the water is leaking out the drain, and I'll watch that ultimately the level of the water in the sink is dropping, or I'm never able to get anything. So I have to increase the water that I'm putting into it in order just to keep it stable. But that's not what we're doing. We're increasing. So I have to turn the water on a lot. The rate has to be huge, much greater than I'm draining it in order to get the water level to rise. That's kind of the same idea, right, that we're doing here. So, uh, so when I calculate this, you'd say, why is the work in here? The work is in there so that we know how much heat we're transferring. It's not that there's work in the entropy change. It's not work that's in the entropy change. It's the amount of heat that we had to transfer in order to get the thing to go from one to two. Okay? It's that amount of heat that we had to put in, and the amount of heat we had to put in is based on how much did we lose and how much do I need to end with? Oh, I need to put in this much. So it's essentially a calculation of heat based on what is necessary. Okay? It looks funny, but hopefully I'm getting you convinced that it's really just about how much there is that I need in order to make the heat that's necessary, in order to transfer the heat that's necessary, and that's what we're using to calculate the entropy change. Okay, that discussion aside, now take a look at what this thing does depend on. This is the entropy change of an ideal gas during a random process. I haven't even said what kind of process this is. In fact, I haven't even told you what kind of gas this is. I still have the degrees of freedom number here. We could be at constant pressure. We could be at constant. No, we can't be at constant temperature. Then dT would be zero. So that's a good offshoot. If I have an isothermal, then this front piece disappears. If I have an isovolume, then this piece disappears. If I have constant pressure, they're both in there. If I have adiabatic, they're both still in there, right? Because there's nothing in here that is dependent on that, right? No, this is all. So it could be anything. This should be a fairly general expression for any process that you want for the entropy change of an ideal gas as you take it through a different process. But notice what it is. It's based on what the temperature change in. Okay, that makes sense, right? It's heat transferring, and that means the temperature could be changing. Okay, if the temperature is changing, great. But if it's not changing, it's isothermal. And that means that the entropy change is really coming about because the gas is occupying a bigger volume. Does that make sense? If I have a confined gas, it can only be in here. It's not very disordered compared to when I let it be in this container. Oh, you can't see my room, but if I'm in the classroom here and I've got this big amount of gas, right? It's essentially like back to that champagne bottle thing with the condensation of the water vapor. If I take that pressurized gas, it's in a small little neck between the champagne and the cork, right? I would say that it has a certain amount of entropy. I have no idea how much it is, nor can I calculate it. Notice, we can only calculate changes. So there's some amount of entropy there, and it's in the small volume within the airspace of the bottle. We pop the cork, this comes out. Oh, it's got a lot more entropy now. because it's able to occupy a much bigger volume. Okay. So the disorder has gone up. Yeah. You can kind of think of it as block stacking. If I take a bunch of blocks, like Jenga blocks or something, I can put them into a nice ordered situation. But notice what happens when they are ordered. The volume is small. I put them all together like this, and I suddenly I fit all these blocks into a tower like this big, right? And then your your toddler comes around, or a tornado, or a hurricane, or an entropy generator comes along and smashes the whole thing all. And then all of a sudden, right, these things are flying everywhere, and they're bigger. Now there's, would you agree that is a more disordered situation, right? Even if you take the small, even if you just push it over, right? Even if you just push it over so it kind of falls like this, it's still taking up more volume, right? So same idea. If I have a volume increase, I'm seeing an entropy increase. Okay, so that's what we've got here. Um, what else do we want to say about entropy? I don't actually want to say too much more. I think it's mostly just it's a little different. Mostly we're trying to use some of the mathematical results to help us develop the conceptualities involving the entropy. All right, so hopefully that's helping develop a mental picture. Okay. So we've done that and we've done this. So what we're going to do now is let's go talk about, yeah, let's talk about heat cycles. All right, let's talk about heat cycles. I want to, I want to do a heat engine. I guess let's look back at some more heat engine stuff, and I want to go back to the reversibility stuff too. So let's start with an efficiency. Okay, let's start with efficiencies. Oh, now I didn't tell you this, did I? Let's start with efficiency. And yeah, we didn't have this discussion, did we? All right. Efficiency, a very basic definition. I learned this when I was in my very first thermodynamics class, and it stuck with me. When that was back when I was first, uh, gosh, it was within my second year, I think, I was at Chico State at the time. So within about the second year of me being in Chico State, I think I was taking the engineering thermodynamics class, and the guy was great. He gave a definition, and it stuck with me. I would say all these years, but since then, I'm only like maybe 4 or 5 years old. So it was only 4 or 5 years ago. The definition of efficiency is what you get out, your desired result, right? It is what you want out divided by what you had to put in order to get that. It's just so clean and so easy. What you want out over what you put in. With the caveat that it's the things you're looking for and the total of the things you had to put in, right? So efficiency basically is this ratio. And so if you keep that in mind, as I have for the past 4 or 5 years, then I don't think we'll go too far wrong. As long as you have a good conception of what it is that what it is that the thing's trying to do and what it is that you had to supply in order to make it do that. Well, let's take a look at a couple of examples of this. Okay. We've been talking about heat engines. or an engine, what is it that we are trying to, what is our desired output? I guess would be the question, right? What is it that we are trying to get from the engine? We want something. We want it to give us something. What is that thing? Let's go back. Let's go back and look at the schematic of the engine. Okay, the engine, as the simplest engine that is allowed by the Carnot statement is this heat reservoir, that cycle, and this heat reservoir. And it's the transfer of heat between the two reservoirs. It has to exchange with at least two reservoirs. So we'll have two heat transfers here. This is coming out of the hot reservoir. That's going into the cold reservoir. And the work is coming out. And I realize the arrows are not really to scale, but you know what? That's the way it goes. You can kind of think of this as a bar chart, right? This is basically a bar chart of energy. You might think of it as something like this. This is not super, because really it's a transfer, but you can kind of think of it as this. This is cheating. I will say that 100%. This is cheating. This is total cheating. Yeah. No doubt about that. Because these QHs aren't energies, they're transfers. So it really should show up as the thing that's going in the arrow. But nonetheless, at least it gives us an idea. From the perspective of the system, I took in QH. I'm going to perform my cycle of an adiabatic with an isothermal and an isobaric with an isovolume, and I'm going to go through and do all my stuff. And now my system is back to the way it was, and I have exhausted QC to the cold reservoir, and I've outputted work to the environment. I've outputted work to the environment. So what is it that we want in an engine? It's the work. That's why we have engines, so that they will do our bidding. The efficiency of an engine then is this kind of Greek epsilon. It's kind of Greek E here. What we have, what we want out. Now, what do we have to put in order to get the work? Well, if we don't have any of this, then we don't get any of that. So what we're putting in is the QH transfer from the hot reservoir. And that's ultimately what the efficiency of the engine is. Now, suppose that we looked at a refrigerator. What about a refrigerator? What is it we want out of the refrigerator? Well, let's draw the refrigerator and see if we can get some, what if we can get some learning out of this? So we're going to draw basically the same thing. Okay. Now I am supplying the work. I'll put it in this way here, like that, and driving heat like so. If I don't supply the work, this violates the Clausius second law. But that's not the only result of this cycle. So it consumed some work from the outside, and it drove heat from the cold reservoir into a hotter heat reservoir. And this is the simplest possible refrigerator that's allowed by the Clausius cycle. The Clausius statement. Okay. So for a refrigerator, what is our desired outcome? The desired outcome is keep the cold stuff cold. So QC is what we want. What did we have to put in order to get that? W. So in the refrigerator, it's QC that we are looking for, and it's W that we put in order to achieve that. Now, here comes the fun time. It's not called efficiency anymore. It's still an efficiency. But this number, we will see this in depth a little bit later, but this number can be greater than 1. This efficiency cannot be greater than 1. It cannot even equal 1. And that's down to what? Carnot's second statement, right? Carnot's second law. This number cannot be 1. If this number is 1, what have we achieved? We have achieved taking everything that came this way and outputting it this way, which means we have not done one of the things that is required of the Carnot statement, and that is to exchange heat with a second. Yep, exactly. There is no second transfer of heat, okay? And that violates the Carnot second law. And now we are realizing we are screwed, because even though that's okay via a first law perspective, right? That's just energy coming in, energy going out. If QH equals W, we have an efficiency equal to 1, everybody's hunky-dory. And now Carnot comes along and says, you can't even do that. You can't even get, you can't, this is like going to a casino. You're going in here and you're sitting down at the blackjack table, and the first thing you realize is that, okay, I'm never going to win. Right? First law is telling you you can only break even. Energy comes in, but then you have to have that energy leave. Okay? It's a cycle. So you have to take the system through its processes and return to the original state variables. So I'm never going to win. I'm going to take the energy in, I'm going to put that energy out. I'm going to break even every single time. Now Carnot comes along, and he puts in the second sign here at the casino table, which is you're not even going to win and you're not going to break even. So the second law is you don't even get back what you had, what you took in. You can't even do as well as 100%. Right? I can't give you I can't make a full 100% transfer of the stuff that I want. I want to take all of this in stuff and give you this, but I'm not even going to do that. I got to throw the rest away. So an efficiency of 1 is prohibited by the Carnot cycle, by the Carnot statement. All right. We can't even do 100%. Now, in a refrigerator, the situation is a little different, and we'll probably get to the analysis of the refrigerator next week. But nonetheless, it's not referred to as an efficiency, because efficiencies we usually think of, well, it's got to be, note the, maybe I'll make that a little bit bigger so you can see it. But note the equals great, note the less than or equal sign here. And note the lack of the equal sign on this side. That's not possible. Okay, so what is this known as? This is known as the coefficient of performance. Or the COP, for short, coefficient of performance. And that's a number that can be greater than 1. In fact, if it's not greater than 1, Your performance is lacking badly. Okay. Sorry, I just got a little pop-up on the screen here. So I would like to get rid of it. And the mouse is, okay, good, now working. Interesting. Okay. All right, so that's a number that can be greater than one, and that's okay. So, I guess what I want to leave you with today is I want to say these three statements. I want to tell you these three theorems, that come out of a little bit more of analysis. I'm gonna erase this abomination. So here are some theorems. And the first one is that the efficiency of a reversible engine cannot be exceeded. Remember, if we're thinking about reversible engines, we're going little bit, little bit, little bit, little bit, no losses, right? If it's irreversible, we're going and there's losses. The first theorem is you cannot have an irreversible engine be better than a reversible one. Makes sense, hopefully? In other words, the efficiency of a reversible engine is always greater. It's not going to be exceeded by a real engine. A real engine is an irreversible one. Okay? Any reversible engine that we have that's operating between the same temperature difference, right? If they have a T hot and a T cold and it's the same, then all reversible engines have the exact same efficiency. So they have the same efficiency. That didn't come out too good. My blue's going to run now. All reversible engines have the same efficiency if they're operated between the same temperatures. Okay? If they're operated between the same temperatures, that's what this says, between the same temperatures. Okay? And the third one is that this efficiency that the engine has decreases as this temperature of the cold gets closer to this hot temperature. The efficiency drops. So I'm summarizing this quickly in shorthand, but the efficiency drops when T cold approaches T hot. If it gets closer to T hot, then the efficiency is dropped. And I think that will conclude our day today. I'm going to leave you with those three theorems. We'll pick up there on Tuesday next week. Keep an eye out for a lab that I'll post tomorrow on, well, I'll run it down. It should be a fun one. It's a little bit of a fun experience, I hope. Anyways, we'll pick up here on Tuesday next week. We have next week of class, and we might sneak in a little bit of a review. I don't know if we will or not, but we have next week of class and then another lab and then the celebration. So it's next week and that's it in terms of classes before the celebration. Oh, and if you don't know what a celebration means, it's the first exam. But it should be a celebration, not a stressful event. It should be a celebration. So with that, I bid you good day. And that will be it for thermodynamics when the celebration happens. Yes, that will be it. And we are moving on to optics. So I bid you good day. I say go increase entropy of the universe because you don't have any other choice. Enjoy your weekend, and I will see you next time.